Hello everyone, Kazi here. Um, Today I just wanted to talk about a statement that you will hear often in physics classes as well as I think electrical engineering, which is that a capacitor blocks DC but allows for AC to pass through. So I wanted to give an outline for why a capacitor behaves as such an element. So actually, if you would like to study any electronic element, you would need to familiarize yourself with the VI characteristic of that element. So in order to even proceed further, we need to uh, analyze the VI characteristic of a capacitor when an AC signal passes through it. So before that, we are already familiar with the establishment of the principle that a capacitor fulfills this equation, right? So if we take the time derivative of this equation, we get a equation that relates the rate of change of voltage and current. So actually, let us imagine that a voltage uh, that we excite our capacitor by passing an AC signal whose voltage is given by the following form. So if that is the case, then dv dt would be I omega v e to the power of I omega t, and so this is I omega v. If we use this here, well, what we get is c times I omega v is equals to I. So we get v divided by I is equals to I 1 divided by I omega c. Now notice something about this. This looks a lot like the resistance terms in Ohm's law, right? When you say V is equals to IR, or we just say that the ratio of voltage to current gives you the resistance. So this term acts very similar to resistance, but this is uh, a generalization of resistance to the AC circuits, and this is something we call reactance, XC. So XC is equals to 1 divided by omega C. Now a question naturally arises that given if our capacitor were excited by say two sinusoidal wave trains of different frequencies, say one omega and say the other omega 2, right? So in that case, what would the reactance be, right? This is an important question to ask because in many practical situations you'll have multiple different uh, wave trains that are exciting your capacitor, right? Or that are applied at the ends of your capacitor. So this is an important question to ask, right? So actually, I'll encourage you to reason through and prove the following: that if the inductance due to just the existence of the excitation omega 1 was x1 and the reactance for the corresponding frequency omega 2 was x2, then the combined reactance would just be the sum of both of these. So since it's the sum of both of these, so we can just write them like the following. So this means that if we had even more number of waves exciting our capacitors, we can just write it as follows, one by one. So if there were n number of frequencies, right? Now, I want to ask the question of what will happen if I excite my capacitor with a DC voltage, right? With a DC voltage, not a sinusoidally varying voltage, but a DC voltage like this. Uh, bu- but the problem with this is we have learned how capacitors are excited when there's a sinusoidally varying uh, pulse that is applied across them, but we do not know anything about how to deal with a function like a constant function that is applied at the ends of the capacitor to excite it, right? There is a way to do it, which is that there's you might recall, and you might immediately jump out in your head that we can use Fourier series and Fourier transforms, which is exactly what we'll be doing now. I'd like you to recall one very important rule. Actually, wait, before that, actually, if we knew that if I supplied a voltage V with time as being a constant voltage V naught, then if we knew what frequency it consists of, then we could fill up the omega 1, omega 2, and so on and so forth, and then we could talk about the impedance of the capacitor for a DC applied voltage, right? So this motivates us to look at how to express a constant function as a sum of sinusoidals, which is what Fourier series and Fourier transform concern themselves with. In fact, the subject of Fourier analysis deals with the study of breaking down functions into sum of sinusoidals, and more generally, actually, Fourier analysis is about breaking down functions as sum of orthogonal functions. But that's a topic for another day. So let us actually recall one very important uh, property of the Fourier transform, that if you take the Fourier transform of a constant function, then you get a Dirac delta. So basically, this tells us that if you want a wave in the frequency space that is localized like this, okay, that is localized at omega equals to 0, then what you will have to do is you have to add a whole bunch of sine waves of all the frequencies, frequencies ranging from minus infinity to infinity, all of the same amplitude 1. You add frequency omega 1, omega 2, omega 3, and so on and so forth to get this localized wave pulse. Now we can actually use this in the other direction as well, because Fourier transform happen to be self-inverse. So you can also make the following statement, that the Fourier transform of the Dirac delta is a constant function. So what does this tell you? It basically tells you that to have a constant function in time, what you need to do is you need to sum of waves of frequencies ranging from minus infinity to infinity, whose amplitude is given by the Dirac delta function. Now the property of the Dirac delta function is such that it only contributes around 0, and all of the other contribution of frequencies vanishes. So basically you can neglect the fact that we are considering contribution from minus infinity to infinity of all the frequencies. You can just say basically that we have to talk about a wave whose frequency is near 0 and whose amplitude is near approximately infinite. That's what the fact that is implied by the Dirac delta. So basically this tells you that with a constant function, the frequency associated is 0. The frequency of a constant wave is 0. So this means that if I come back to the impedance formula that we derived, 1 divided by omega 1 plus 1 divided by omega 2, and so on and so forth, it turns out that only the omega near about 0 contributes, and so it becomes 1 divided by, it sort of becomes 1 divided by 0, and so your impedance approaches infinity. So this is telling me that the resistance that the capacitor offers for DC is infinite. So it effectively does not let any DC current to pass through, and so this is what we mean by a capacitor blocking DC. Thank you. I hope you learned something from it.